At this point, we've identified a lot of vector spaces just sort of as very general objects in kind of the mathematical world. But vector spaces actually show up on their own, specifically in contexts that we've been working in. For example, if you solve a system of homogeneous equations, you get a collection of vectors. So if we write down the collection of solutions for this kind of system of equations, let's call that collection of solutions S. So this is all solutions. We could ask, is this collection a vector space? So one thing that we'll have to notice is what kind of objects are all solutions. So because I'm missing all of my x's here. I need my variables to have a system of equations. The types of things in S, these are going to be vectors in, these are all in Rn, right? Because a solution is a value for each one of these variables, and so a solution is just going to be a list of numbers. And so if we arrange them in a column, then we do get a column vector. One thing to notice is that although every solution in this setup, every solution is a vector in Rn, not every vector in Rn is a solution. So careful there, right? Okay, so let's check to see if this collection of solutions is to this homogeneous system is a vector space. Well, right, we already, since these vectors are all in Rn, we already have a sense of addition and scalar multiplication. But one thing that we can't at all be sure of is closure under addition. So how could we check that? Well, remember, we know a lot about what a collection of solutions to a homogeneous system looks like. We know that a collection of solutions to a homogeneous system looks like this. We have these fixed vectors v1 through vk. And if we take any combination of them by multiplying them by scalars and adding them up, so here a1 through ak, these are all real numbers. Right. Every solution, we can find fixed vectors v1 through vk so that every solution looks like this, and everything that looks like this is a solution. So to check closure, we can add two of these together. So say we can take a1 v1 through ak vk and add it to another vector of the same form. So I can't reuse a, so I'd better use maybe b, b1 v1 up through bk vk. And these v's are the same v's, right? The whole point of this, all the work that we went to figure out the structure of a collection of solutions for a homogeneous system, the whole point was that these vectors, you find them once and then that's it. They're fixed. Those vectors are always the same. It's just the coefficients that change to give you different solutions. So the coefficients in this second one here are different. They're the b's, but the vectors v are the same. Okay, so since these operations are all vector addition coming from Rn, it is safe to remove the parentheses and rearrange things. That's the commutativity and associativity of vector addition. And when we do that, we get a1 v1 plus b1 v1, and so on, down to ak vk plus bk vk. And then, of course, because this scalar, all of these scalar products and all of these vector additions are all in Rn, we can do distribution backwards. In other words, we can factor out all of the common pieces. So that gives us A1 plus B1, B1 plus, and so on, down to AK plus BK, VK. There we go. All right. So we took two solutions to our homogeneous system. We added them together. Did we get another solution? Well, this solution is exactly of this form. Instead of A's, it has A's plus B's, but still it's all of these vectors V times scalars all added up. So this is in S. So that means that we do have closure under addition. That's kind of the hard one. Commutativity of addition, well, we get that for free because we're using the vector addition from Rn. Same thing for associativity. For existence of an additive identity, well, remember, in Rn, the additive identity is the zero vector. So is the zero vector in this collection of solutions? Well, it is. If you choose all the A's to be 0, you get the 0 vector. So, so we do have a 0 vector in our collection. Do we have additive inverses? Well, yeah. Since any choice of coefficients here gives you a solution, you can also flip the signs to make the negative choices. So that gives you an additive inverse. Closure under scalar multiplication, that's worth checking. So if we have a solution, A1, V1, up through AK, VK, and we multiply it by a scalar, is the result a solution to this homogeneous system? Well, distribute, we get RA1, V1 plus dot, 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 down to RAK, VK. So I've distributed and used the associativity of scalar multiplication. But this result is exactly in the form that it needs to be in to be a solution of the homogeneous system, right? It's scalar coefficients times these fixed vectors V. So that gives us closure under scalar multiplication. And then the rest of these we get for free because we're working inside of Rn. So the upshot of all of this is that the collection of solutions to any homogeneous system of equations is a vector space. In fact, we'll see later that this is actually a very rich source of vector spaces. As soon as you write down a homogeneous system, you have a vector space, the vector space of solutions of that system. Let's have a look at another kind of equation that you might have run into, a differential equation. So here, this is a very simple differential equation, but we can ask ourselves about the collection of solutions of this differential equation. Do they form a vector space? Well, any solution is going to be a function from the real numbers to the real numbers. And we already know that the collection of all functions from the reals to the reals is a vector space, right? It has pointwise addition and scalar multiplication as its vector operations. So what this equation is doing is essentially choosing or selecting a subset of functions from the reals to the reals. The functions that, first of all, are differentiable, have derivatives, and also satisfy this, this equation. So do they form a vector space? Well, you know, a lot of these things we're going to get for free as long as we have closure under scalar multiplication and addition. So let's check those two. So suppose that we have two solutions to that differential equation. So suppose, actually, let me make this differential equation a little more interesting. I think it's too boring even to bother with. This differential equation is a little more interesting. So let's suppose f and g are solutions to the differential equation. Okay, we need to know, to check closure under addition, we need to know, is f plus g a solution? So how could we check? Well, I mean, to check if something is a solution, you can just plug it in, right? So let's plug this function into this equation and see if we get 0. So derivative with respect to x of f plus g plus f plus g. And what we're hoping is that this is going to be equal to 0. We don't know if it is equal to 0 yet, but that's what we're hoping. All right, well, this derivative operator, right, because we have a sum here, we know derivatives, we can use the sum rule for derivatives to essentially distribute this derivative. So we get derivative of f plus derivative of g plus, and then f plus g. Okay, well, it would make sense to group these so that the f's were together and the g's were together. So derivative with respect to derivative of f with respect to x plus f plus, and then we have the derivative of g with respect to x plus g. All right, well, remember, we were hoping that this would come out to be 0. So is there some reason that this should be 0? Well, remember, f was a solution to this differential equation, right? Up here, f is a solution to this differential equation, so that means the derivative of f plus f itself does equal 0. So that means these first two parts add up to 0. But by the same token, g is a solution to the differential equation, so that means that dg dx plus g is also equal to 0. So altogether, we get 0. So that means that the answer to our question, is f plus g a solution to the differential equation? The answer is yes, it is. A very similar argument will show you that solutions to this differential equation are also closed under scalar multiplication. Essentially, you move the constant multiple outside the derivative and then do some factoring. So I'll let you fill in the details, but this collection of solutions to this differential equation is also closed under scalar multiplication. All of these other properties, these are purely algebraic properties that our collection of solutions inherits from the larger collection of all functions from R to R. So that means that we have a vector space. So for this differential equation, at least, the collection of solutions forms a vector space. I'll warn you that the collection of solutions, it's not the case that the solutions to every differential equation form a vector space, but nice differential equations do have vector spaces as their solution sets.